Hi guys, this is Saka, and I know there's been a lot of confusion with some of this intermolecular force stuff. So I'm here to kind of help trying to clarify some of these things. This one is an overview over all of the intermolecular forces, and then there'll be one on just polarity and whether something's polar or not. So we'll do that in a minute. But let's first go over the intermolecular forces. So the idea here is that all this polarity business, all this intermolecular force business is based upon um, the way the different molecules can interact with each other. And so before we can figure out how they interact with each other, we have to look at the elements that make up these compounds first. So electronegativity, which we talked about today in class, plays a big role in this. So electronegativity has an effect on ionic and covalent bondings. So as we said today when we were doing the worksheet, if we have big differences in electronegativity, we have an ionic bond. And this is because the electrons shared between two atoms combining together isn't equal. Okay? So if we look at these polar covalent bonds like between H and Cl, so you see this distribution here, right? The black dots represent the nucleus. The blue triangle represents where the positive charge lies, and the red circle represents where the negative charge is. And we talked today about differences in electronegativity. We know that chlorine is more electronegative based upon where it is on the periodic table relative to H, and because of that, this end is slightly negative and the hydrogen end becomes slightly positive, results in polarity. And because the difference between H and Cl is an intermediate value, and because they're both nonmetals, this is a copolar covalent bond. If you look at the two where they combine with themselves, there's no difference in electronegativity because they have the same electronegativity values. And notice that the triangle and the dot is basically in the same spot, implying that there's no difference in electronegativity and that there's equal sharing of the bonded electrons, resulting in a nonpolar covalent bond. Polar covalent bonds, we'll talk about what it means to be polar a little bit later. But here we have, essentially what it is the bonding electrons are unequally shared. And what that means is that the more electronegative element, its nucleus pulls the shared electrons closer to its own nucleus than the nucleus of the less electronegative element. And what results is a slightly positive and negative end. So these things that look like incomplete eights are actually lowercase deltas, and usually we use these in conjunction with a plus or a minus to indicate positive and negative ends on polar molecules. There are some compounds that are not polar overall despite having polar bonds, and we'll talk more about that as a separate podcast. And here, polar compounds are soluble in water because water is also polar itself. And again, the positive ends are where the electron pairs are not very close to, and the negative end is where the more electronegative element in the bond lies. Okay. Properties of covalent compounds. So these intermolecular forces are very important for covalent compounds. For ionic compounds, there's only one force that holds them together, their ionic force. But for covalent compounds, we have to look at them a little bit more closely to figure out how they're interacting with each other, because this influences some of their physical properties like boiling points and melting points and what state of matter they exist in. So there are three different kinds of intermolecular forces for covalent compounds. The strongest is hydrogen bonding, and this is something specific for polar compounds that contain H. Dipole-dipole interactions are almost as strong as hydrogen bonding, and this is the result of polar covalent compounds that do not have hydrogens in them. And then dispersion forces are the weakest force, and we'll talk more about what they are. And this is the only force nonpolar compounds exhibit to hold themselves together. But if something is polar, they'll also have dispersion forces, but they're there, but it's not what holds them together primarily. Okay, so let's talk about each of these individually again. So hydrogen bonding basically is the attraction of hydrogen in a polar molecule to a lone pair of electrons from another polar molecule itself. So you see these dotted lines here that seem like they're connecting the H from one molecule to the O of another water molecule. These dotted lines represent these weak forces that are hydrogen bonds. So this hydrogen is attracted to the unshared pairs of electrons that are part of this oxygen. Okay? In order for this to work, H has to be bonded to either F, O, or N to form a hydrogen bond. If it's anything else, the odds of it being a hydrogen bond is pretty low, because there wouldn't be a big enough difference in electronegativity for it to be polar enough. This is the strongest intermolecular force. So this is the strongest force that could hold polar covalent compounds together. It is not, I want to emphasize here, it is not as strong as a covalent bond. It is not as strong as an ionic bond. It's a very, very weak force in comparison. Thousands of times weaker. But if you add them up over thousands or millions of molecules of water, they add up to be quite strong. So again, we're talking about certain kinds of molecules. And some of these things you might remember from your biology classes. If you remember your adhesion, when water clings to like the glass to make the meniscus. Cohesion, when water interacts with each other. So that's why you're able to pour the water over the cup, over the top of the cup. And surface tension, which is another reason why like bugs can play around on the top without falling through. Dipole-dipole interaction. So this is the idea here, where it's like a weaker version of a hydrogen bond, but the two things that are interacting together are not necessarily hydrogen. Because this one's a dipole-dipole because Cl isn't on our list. So even though they form a polar covalent bond, is not necessarily like the difference isn't strong enough to be in the hydrogen bond range. Okay, the idea here, it's the same general idea where the positive pole of one molecule is attracted to the negative pole of another molecule. It's very similar to hydrogen bonds, but it's not as strong. And the polar molecules that don't have H connected to one of those things I listed earlier will exhibit dipole-dipole interactions. And again, this is something only polar covalent bonds can do. This last one here is dispersion forces. Sometimes it's known as London dispersion forces, and it's a weak covalent bond. And the idea here, it's not a weak covalent bond, it's a weak intermolecular force. And the idea here is that we know that electrons are moving around constantly within around the atom, right? And the idea here is that you'll get times where the electrons are distributed in such a way where it looks like a polar covalent molecule. So you end up getting these what they call transient dipoles, and they're transient in the sense that they exist for a few seconds and then they immediately fall apart because the electrons are in constant motion. So you'll get these temporary dipole interactions that exist, but what ends up happening is because the electrons are moving around so much, it doesn't last for very long. And the idea here is that this is a very weak intermolecular force, but if you add them up, they can end up being quite strong also. So like for instance, long molecules of oil, which are just basically long carbon and hydrogen chains, you can add up all those dispersion forces and it's good enough for it to liquefy or even solidify to form like vegetable oil or like something like butter, which is a solid fat under the right circumstances, and that's because of the dispersion forces that help hold it together. Anyway, that's it for now, and I'll come back in a little bit to do some polarity stuff with you.